Hello, everyone, and thank you all for joining us today. I'm Bob Crossan, Senior Managing Editor for Water and Waste Digest. On behalf of Water and Waste Digest and our sponsor, Fluid Components International, or FCI, I'd like to welcome you to today's presentation titled, Don't Get Bent Out of Shape Due to Poor Meter Runs. This webinar will cover the ways that piping constraints can lead to inaccuracies in your gas flow measurements. Inaccuracies lead to insufficient processes. Inefficient processes lead to increased operating costs. Fortunately, these problems can be solved. Solutions exist for improving accuracies under less than ideal conditions. However, not all solutions are alike. Depending on the technology, there could be some hidden costs that could impact your overall cost of ownership. So today we're going to learn specifically three things. You will learn how to understand piping conditions that can lead to inaccurate measurements. You will understand the added value of utilizing flow conditions, and you'll gain awareness of the hidden costs of permanent pressure loss. We'll get started here in just a couple of minutes, but first, a little housekeeping. You'll notice on your viewer you have the ability to ask questions. We really encourage you to ask as many questions as you would like, and we will get to as many as we can before the time ends at this webinar. Any questions that we don't get to today, we will answer offline. Now today, our presenter is Art Womack. He is the Business Development Manager for Fluid Components International, and he has 24 years of experience in the design, production, application, sales, and marketing of flow level, pressure, and temperature process instrumentation. He earned his BSEE from Rose-Hulman Institute of Technology in Terre Haute, Indiana, and he has authored several articles and technical application bulletins as a senior application engineer over the course of his career. His current position is Business Development Manager for Fluid Components International, a provider of thermal flow level switches, thermal mass flow meters, and flow conditioners for process industries including energy, oil and gas, chemical, municipal, and others. And with that, I'd like to turn it over to you, Art. The floor is now yours.
All right, thanks, Bob. Well, Bob, as you said, we appreciate the opportunity to be here today and discuss issues that come up when we have poor meter run conditions. Here at FCI, we and our channel partners have supported the municipal industry for over 50 years. For the past 15 years, I myself have been working with a multitude of engineers, contractors, and end users involved in the water and wastewater treatment. A good portion of that work ties into common gas flow applications such as blower systems, aerobic digestion, odor control, ozone generation, and flares. One of the more common challenges engineers face regarding accurate flow measurement is insufficient straight run. With that, there's an associated issue tied into permanent pressure loss and how it affects energy costs. So when we talk about inadequate straight run, really we're looking at what's happening with our meter accuracy. Are there inaccuracies being introduced? My performance in the field is not matching up with the manufacturer's specifications. Then we talk about the associated pressure loss. The technology that I'm selecting, whether it be the meter or as we look at it, flow conditioners, what's it doing as far as wasted energy goes? Am I losing pressure in my system that I don't want to lose? So it's kind of the items we're going to look at here today. So when discussing accuracy, I always like to categorize things as the ideal world versus the real world. Published flow meter accuracies for most technologies, regardless of the manufacturer, are based on fully developed laminar or turbulent velocity profiles. And when you look at these specifications, within a brochure, you got to keep in mind that these are always best case scenarios. It is worth repeating that the performance parameters for any flow technology you select are based on these ideal lab conditions. Everything's tightly controlled. You'll see things such as reference meters of a higher accuracy than the meter being tested, creating known flow profiles that are appropriate for the application process conditions, plenty of straight run, clean and dry gases, and flow stands that are being used that had the measuring range for the application so your flow turn downs met. Many of today's common flow instrumentation utilize a single point measurement approach. For those technologies, calibrations are made based on the maximum velocity of a fully developed laminar or turbulent flow profile. And you can see that even between those two, that maximum velocity point can vary. So anything in our piping that disturbs that flow profile will come across as an inaccuracy in our measurement. Same goes for if we're in the Reynolds number transitional zone. Next two slides have a few examples of adequate straight run based on common obstructions. We're talking about elbows in or out of plane, upstream or downstream flow control valves, reducers, pipe adapters, various things. Our recommendation over the years has always been to allow 20 pipe diameters upstream and 10 pipe diameters downstream to achieve the profile needed for that accurate measurement. Having 30 pipe diameters of straight run in smaller line sizes usually isn't a challenge. When you start getting into 12-inch or larger line sizes, a lot more real estate is required. However, there is a bit of forgiveness in the straight run requirements for larger line sizes for some of the common obstructions we see, illustrated in these two slides. To help illustrate what a fully developed turbulent flow profile looks like, we've used computational fluid dynamics analysis tools to generate these next few images. The lower velocities you see are in dark blue, the higher velocities in red. When you look at this cross-sectional view, you can see that we have a profile that's uniform in both axes, and this really represents the ideal conditions that are used in the calibration of gas flow meters. What we see quite frequently is that the ideal lab conditions and applications in the field don't always line up. Sometimes there's a focus on larger capital equipment. Metering is more of an afterthought. There's coordination between the mechanical engineers and the electrical engineers and instrument engineers to make sure things get laid out appropriately. So when you look at aeration, anaerobic digester flares, and natural gas trains, a lot of times what you'll see is compact footprints, valving, elbows, just common obstructions you'll see in your system. Part of the challenge we see is getting our hands around what impact various obstructions will have on our flow profiles. In almost every case, we see the velocity seen at the center line of the pipe no longer matches up with the maximum velocity the instrument was intended to measure. Depending upon the obstruction and its location, we can be reading higher or lower than expected. So one key piece of information we need to know when reviewing our piping conditions is what will be an acceptable level of measurement accuracy. Is it 1%, 5%, 10%? A lot of times design decisions will come down to how repeatable the measurement will be, even if the accuracy is impacted. So next, we're going to look at a few of the more common obstructions and see what changes occur in the velocity profiles. And we'll see what get an understanding of the impact on each as it has on accuracy. Here we see a 90-degree elbow that is 4 pipe diameters upstream of the meter location. We can see that the higher velocities skew towards the top of the pipe. Although this type of obstruction is very benign, we do see an additional inaccuracy. As you look at this slide, you can see that we don't have that fully developed, roughly bullet-shaped flow profile condition occurring. So even at 4 diameters upstream, we could see an impact on our accuracy as much as 4.3%. The next thing we look at is just moving that elbow downstream, moving it down 2 diameters, keeping 20 diameters upstream. This one, doesn't have as great an effect on the impact of the flow profile. You can see here that it's close to what we would consider that ideal condition, still not fully developed. So there is some effect with inaccuracy, and we see that inaccuracy being in the range of 0.8% in this piping condition. Definitely an improvement from when it was upstream. Here we have a convergence from larger to a smaller pipe that is located 4 diameters upstream. We can see that the velocity profile is similar to ideal conditions, but we do have some slightly higher velocities through the center of the pipe at the meter location. Like our elbow, it's fairly benign, but will still impact our accuracy. And in this case, that convergence is going to impact it by roughly 1.3%. Next, we'll look at the upstream obstruction that creates one of the greater challenges when it comes to accurate metering, modulating butterfly valve. Here we have a valve that is 5 diameters upstream of our meter location and is 50% open. You can see how the velocity profile is skewed significantly in both axes. The resulting profile is not even close to the ideal condition. We're at the lowest velocity at the center of that flow profile, compared to being that maximum velocity. Given that it is being used as a control device, the velocity profile will vary by the position of the disc. So looking at worst case conditions, we would see an additional measurement inaccuracy up to 15%, which in a lot of cases is very significant. Moving that same butterfly valve downstream of the meter improves accuracy tremendously. However, we still have impacted the accuracy by another 1.7% because that actual profile is still slightly, distorted compared to the ideal. But it has made that significant improvement in our measurement. The last model I want to share today is a combination of these obstructions. We have a convergence and modulating butterfly valve upstream and a 90-degree elbow downstream. Given the prior examples, we can see that the impact of each obstruction has an effect on the velocity profile at the metering point. And you can see here again, the lowest velocity is towards the center line of this measurement we're trying to make. So our profile is very distorted. And actually in this condition, we're looking at a worst case accuracy impact of 18%, because that's going to vary depending upon the valve position. So all of these examples illustrate that the type and location of an obstruction will impact your overall measurement accuracy. Moving them closer to the metering point will further magnify those errors, and moving them further out will help minimize them. So taking another look of an example, less than ideal straight run. By modeling, we can get a decent estimate of what our accuracy and uncertainty will be. This next example here represents a typical aeration or blower application with an elbow upstream, 11 diameters, a butterfly valve at 8, and another 90-degree elbow, 4 diameters downstream. Our model in this instance is suggesting an overall application uncertainty estimate of 8.76%. which is significantly different than the published instrument accuracy of 1%. For the given example, the flow is going to be turbulent, and based on having a modulating butterfly valve upstream, we inherently know that the meter accuracy will be affected by the position of the disc. We no longer have the rounded profile associated with a fully developed turbulent velocity profile. Velocities at the wall of the pipe are going to be much higher than those in the center line in most cases. So what can we do to improve meter accuracy if we are unable to rework our piping design? So let's consider using a flow conditioner. So in the same configuration as before, we're using in our model a flow conditioner located 3 diameters downstream from the upstream from the metering location. That's represented here by the yellow box. The addition of a flow conditioner has improved our overall uncertainty estimate from 8.76% seen in the earlier slide to 1.04%, much closer to the published accuracy of the instrument. When a higher level of accuracy is required in our measurement, this is a very sound approach to achieve our goal and also help reduce the footprint required for our meter run. Purpose of any flow conditioner is to take that less than ideal velocity flow profile and make it more uniform and repeatable. The device is going to allow for a flow meter to more accurately measure gas flow when piping conditions are poor. In many cases, it'll allow you to reduce the footprint of your piping in lieu of designing longer meter runs. Typically, the choice of using a flow conditioner in an application comes down to, required accuracy of the flow measurement. So we're going to look again at our earlier example where we had convergence butterfly valve upstream and an elbow downstream. And keep in mind that no flow conditioner is going to create a perfect laminar or turbulent velocity profile. The objective is to create a repeatable profile that can be accurately measured. So in this instance, we've put in that flow conditioner. You can see it upstream of the meter, downstream of the valve. So as you can see here, we don't have a fully developed flow profile, but we're much closer to the average velocity. And by properly calibrating our instrument to this new profile across the entire flow range, we can greatly reduce the amount of error introduced into our readings. So in this case, we went from 18% being our worst case to bringing it down to a very acceptable 0.8%, just by utilizing the flow conditioner in the application. Now, greatest value is typically achieved when the flow meter is calibrated for that specific flow conditioner profile. As such, distance between the two meters, between the meter and the flow conditioner should be optimized, and manufacturer recommendations should be followed. Otherwise, you're going to still notice inaccuracies in your reading. And before we wrap up today, one thing I'd like to take a quick look at is the permanent pressure loss associated with our flow measurements. In this example, we are again looking at the use of a single point insertion type meter. So given the constraints, we see another large example of inaccuracy due to the location of the butterfly control valve being only 4 diameters upstream of that metering point. So when we take a look at insertion type meters, we can see that the permanent pressure loss can be very low. And here at full flow of 5,500 SCFM, we see that it's less than 1/10 of a pound of pressure loss. Given this benefit, technologies that require a restriction of the line size to make a measurement are no longer preferred. Insertion type technology is very attractive when it comes to minimizing wasted energy or in low pressure processes like digester gas applications. So now we're going to take that same model, we're going to introduce our flow conditioner. Again, we've seen here that we've greatly improved the flow measurement accuracy through this approach. It's almost back to manufacturers' published accuracies. However, we have now introduced a new obstruction that's going to impact the permanent pressure loss associated with the measurement. So when you look at a pressure loss curve for the combination of the devices, the overall pressure loss has jumped from 0.087 to 0.61 psi. We see that roughly 86% of the pressure drop is related to the flow conditioner. This then raises the question of whether or not there are some designs that introduce less pressure drop than others. There are several designs on the market that perform the function of flow conditioning. A few of the more common designs you'll see include tab types, plates, and tube bundles. In every case, the goal is to take a distorted velocity profile and straighten it out so an accurate measurement can be made when there's limited straight run available. Just trying to create this repeatable flow profile. However, each design is going to vary as far as permanent pressure loss go. Head losses are associated with the frictional resistance of the piping system and its components, such as pipe, valve, fittings, etc. Flow conditioner designs introduce varying frictional resistance and can be put into perspective by understanding the number of heads associated with each. As you can see from this graph, the head loss of different designs can range from 0.8 all the way up to 20. Going back to our more recent example, this next table summarizes the permanent pressure loss for a few common designs to help further illustrate how they will impact your system performance. Additional pressure loss can vary anywhere from 33 to 90% higher when compared to the minimum achievable head loss design. So I'm flying through this thing. So to quickly summarize today's workshop, a little bit short here. We want to look at our inadequate straight run. So some of the things we ask, what is the maximum acceptable accuracy for my application? If I don't have adequate straight run, how can I understand the impact of my readings? If my accuracy requirements are not met, will a flow conditioner help me meet my objective? It is not a given, so it should still be evaluated. On the side of permanent pressure loss, are we wasting energy or robbing our process of working pressure? We want to look at things such as, does the selected technology I'm using for this flow measurement minimizing my pressure loss? Does the same go for a flow conditioner if utilized? How much pressure loss is acceptable? So to finish and just wrap up, we do want to hear from you. We do have ways to reach out to us. You can email us through chat today. You can go to our website, find your local rep. They'll be happy to help you. We have some additional email material we can send you. We've got an air gas flow measurement solutions handbook we can send out. We are going to be sending out a newly launched municipal application guide to everybody attending. Other copies can be requested here, and we do ask that you join us on LinkedIn.
Great, thank you, Art. I'll move on to the questions here, just so we can get going with those. As a reminder to everyone who's watching, we do ask that you send in some questions and whatnot. We're going to try and get to as many as we can. We've got a lot of time that we can work with right now, so we're going to start with this one. Are particular flow measurement technologies more susceptible to these inaccuracies, Coriolis, thermal, DP, etc.?
Well, I think what you'll see is based on the technology, you got to look at each one because there are varying recommendations for distances upstream, downstream. A lot of the technologies used, again, are looking at that center line measurement. When you look at insertion types, then there's others that, you're restricting the flow. But they do have in common, there is some requirement for straight run to make sure it's ideal flow. Coriolis is probably more forgiving than any technology out there when it comes to that gas flow measurement. I think the key here is to understand, based on your ideal technology, the one that meets your process conditions, the one that meets your turn down requirements, whether it's volumetric or mass flow. Just understand what that impact is.
Mm-hmm. Cool. Next one we have here is, can I install a flow conditioner in an existing meter run without any issues?
It's a good question. One of the things you look at, going back to what we talked about today, is that flow conditioner is not immediately creating that turbulent or laminar flow profile. That flow conditioner is taking a widely inaccurate, disturbed flow stream and creating a very repeatable condition. So if you already have a meter installed and you put in a flow conditioner, yes, you can probably see some improvement in the repeatability of your measurement, the accuracy of your measurement. But you're still going to have some inconsistencies because that technology may be still looking to measure that maximum velocity, and the flow conditioner is really kind of evening it out, making it more of the average velocity. So ideally, you're addressing this flow conditioner need on the front end.
Yeah. So one of the follow-ups on this question was about the requirements of a thermometer, for example, and you're talking about that unique velocity that you had mentioned. Does that change based on the different technology types as well, or is it kind of you need to keep that in mind when with this?
Again, I think based on technology and different manufacturers, you'll be seeing, different recommendations. Some technologies, are a little bit more forgiving because they're not taking that center line approach. But again, you still have to look at, are they meeting my overall measurement objective? You got to beware selecting a technology based on one factor alone. But when you look at, our side of it, a lot of it comes down to specmanship. You'll see recommendations from a manufacturer of the same technology that vary from manufacturer to manufacturer. And a lot of that is just based on specmanship, trying to position ourselves. You just got to keep in mind that the physics of that flow measurement are the same for everybody,
Mm-hmm.
So hopefully that addresses that question. If there's further follow-up, we can get into more detail.
Yeah, you can't change Mother Nature. You have to play
No,
within the realm of Mother Nature,
exactly.
right?
Physics are physics, right?
Yeah, exactly. Another one here. Are there any common field conditions that can lead to inaccuracies in flow measurements?
Common field conditions. Yeah, I mean, again, the biggest thing we see is obstructions. When we talk about inaccuracies, and in fact, the question came up just this morning before this workshop. Somebody has a meter that's not giving them the reading, but the first thing out is there's a control valve upstream. Well, did we account for that control valve? Piping does tend to be one of the largest issues. The other thing we run across is, even for properly calibrated instruments, we've got to have the process data being correct. Do we have the right flow range, pressure and temperature conditions? Line size even can be an impact. If I calibrate for a 10-inch line and it's actually installed in an 8-inch line, I might have to make some meter configuration changes just for that one condition. The other area we might get into is an application that might have entrained moisture. Those things create some inaccuracy issues. Piping is just one of those things we want to look at when evaluating an application.
Mm-hmm. What about with regarding that same question? What about wet gas considerations in that regard?
Well, wet gas considerations, I think, is an issue for almost every technology. All technologies have their advantages and disadvantages. And, dealing with wet gas seems to be a common concern across the technology board, especially, making sure that the gas itself is not going into a dual phase mode, which is difficult for anybody to measure. Really, it comes down to, having an understanding of what might be creating that issue. Can I dry it? Can I, use a knockout, remove it? If not, what technology is available to minimize the impact of this moisture in my process? When you look at thermal devices, they're working off of a cooling effect. So we have to be careful. But even if you look at older technology, like a differential pressure flow measurement with an orifice plate, the orifice plate's got to be designed in a way knowing that this, wet gas condition can be occurring, because it'll impact its accuracy and measurement as well.
Mm-hmm. Yeah, got it. Moving on to a different one here. Do you see more inaccuracies when the system varies in flow rate, especially immediate changes of flow? Would the conditioners help more on the higher or lower velocities?
If I understand this correctly, we're just looking and seeing what impact it has at the higher end versus the lower end, when I use that flow conditioner. Sometimes it depends on the design. Some of them create a very uniform profile across the entire flow range. Some are geared to that profile may vary, from a low flow condition to a high flow. In either case, again, the true benefit of this measurement using a flow conditioner is having that meter set up for that profile, regardless of the type of conditioner you use. Otherwise, there's just going to still be some residual inaccuracies, and those flow conditioners are going to improve things on both the low end and the high end. You're looking at overall accuracies across the entire flow range of that application.
Got it. This next one, what are the flow characteristics or effects of a pinch valve as compared to a butterfly valve?
I'll be the first one to admit that I didn't take a close look at that measurement, that particular case. Just knowing the nature of a pinch valve versus a butterfly valve, it too is going to have some associated, variance as the velocity profile changes to the position of that pinch valve. Something we'd have to analyze, something we'd have to spend more time on. Like I said, I do know it's going to be impacted. That flow conditioner is going to make a better condition out of it.
Yeah. Well, we can, and I'm sure that you could get some data to send to them after the presentation as well.
Absolutely, absolutely. We'll take a little bit stronger look at that. Go back and do a little bit more CFD.
Yeah. Next one here. How do flow conditioners impact custody transfer metering? Is there any special certification required?
Now, that's a good question. We have provided flow conditioners for manufacturers of other technologies for use in custody transfer applications. In fact, we have, a customer that uses both two bundles for their economical solution, but then when you get into pressure loss and higher accuracy requirements, they go to a tab type, which is, what we offer. And those are all custody transfer. They can be ultrasonic, they can be turbine. Our technology from a metering standpoint is not custody transfer, but we have worked with those others in that application. And, I personally can't speak to whether there's like AGA or other, API requirements. We'd have to do more further research and be happy to do so on the side.
Cool. Well, appreciate all of your time today, Art. This is great, and we've got a lot of information here. And for everyone who is watching, thank you so much for attending today. That wraps up this webinar and the question and answer period. Anything that we didn't get to during this webinar, we will get to offline. And on behalf of Water and Waste Digest and our sponsor, Fluid Components International, or FCI, I would like to thank you all for your participation and staying engaged. This webinar will soon be archived at the URL that you used to access the webinar today, and it will be on www.dmag.com. So you can view it on demand anytime you wish. Just use the same URL today or find it on our website, click that and go to it. Share it with all of your friends. Make sure that they get this information as well. And with that, so long everyone. Stay informed and stay well.